Well, hello, ladies and gentlemen. Mr. Eicher here, coming with lesson number 4 on probability. This is about conditional probability and independence. In a recent year, fans at Arizona Diamondbacks home games would win 3 free tacos from Taco Bell, yummy, if the Diamondbacks scored 6 or more runs. In the 2012 season, the Diamondbacks won 41 of their 81 home games and gave away free tacos in 30 of their 81 home games. In 26 of the games, the Diamondbacks won and they gave away free tacos. Let W equals the event of they win the game, home game, and T is the event that free tacos were given away. Choose a Diamondbacks home game at random from this set of 81 that we're just talking about. So the first thing, summarize these data in a two-way table. I'd encourage you to pause the video and see if you can come up with what are the two variables and how would we come up with the table. So the first variable, I guess we'll talk about home games. So did they win, yes or no? So I'll put home games, a home win, yes or no? Yes, no. The other variable as a two-way table, there are variables here. Give away free tacos. Free tacos. And we'll put yes, no. And then we have our totals. Total column over here, total column over here. All right, so from this information, we have they won 41 of their 81 home games. So home game win, they won 41 total home games out of 81 total home games. So that would be right like that. Next, we have 30 free tacos. So 30 times they were free tacos. And then we have in 26 games, it was both. So 26 would be the yes and the yes. And there we go. There's our two-way table. We can do a little adding and subtracting. 26 plus 4 is 30. 26 plus 15 is 41 down the column there. 30 plus 51 is 81. And then you have a 40 here, and you have a 36 here. So there's our two-way table. We're also asked to do a Venn diagram. Again, on the AP exam, you wouldn't be asked to just create these. You just jump right into questions. These are helpful tools to use to answer probability questions. So here's our Venn diagram. Start with a rectangle. Everything in this rectangle, there's 81 home games represented in this rectangle. The first circle we have, we'll let that be that they won their home game. And then this other circle that we have, this will be that free tacos, so T, free tacos were given away in that home game. It's really helpful when you have Venn diagrams to start with the overlapping region, this overlap region right here. Oh, sorry about that. Pardon my dog barking there. So start with the shaded region. So that would be 26 is the overlap. So 26 goes right in here. Now the 41 wins, do not put 41 here because 41 plus 26 is 67 wins. They didn't win 67 times. So we actually need a number like 15. 15 plus 26 is 41 wins. And then the same idea on the other side, there were 30 free taco distributions. So that would be 4. 4 plus 26 is 30. So everything in this T circle should add up to 30. And then on the outside here, that would be that they lost the game and there were no free tacos. So they had 81 total games. So if we subtract 15 and 26 and 4, how many do we have left over from that? Looks like 36.
So there were 36 games where they lost and there were no free tacos. Okay, so we have our Venn diagram and our two-way table. Let's answer some questions. Probability W, probability they win. That would just be 41 wins out of 81. That's pretty simple. Didn't really need a two-way table for that. Probability that there was not, right? That little symbol right there is not T. That there were not free tacos, so that would be a no on free tacos. And then probability of win and, this is the intersection, so winning and free tacos. That would be the overlap, and I have shaded in green. Basically, this is asking about the overlap, the intersection on the Venn diagram. That would be 26 out of 81 games. Also, that's the yes, yes column in the two-way table. And then lastly, this last one is the intersection, but not the intersection. So everything other than the intersection. So one way you could do that is you could do 1 minus the probability of the intersection. That would be the complement. So 1 minus 26 over 81, which is 55 over 81. 55 over 81, that would be 36 plus 4 plus 15 is another way that you can think of it. Adding everything in the Venn diagram or the two-way table that is not the intersection. So like all that. So those just a couple, again, just getting you used to notation. Letter C, find the probability the Diamondbacks win or there are free tacos. And I included the notation. The or is a union, the U symbol there. So that would be probability of win or free tacos were given. This is the general addition rule. So you have probability they win plus probability there are free tacos minus they win and there are free tacos. We want to count the overlap, but we don't want to double count it. So what happens is probability of winning is 41 out of 81. Probability of free tacos is 30 out of 81. But we have to subtract the overlap of 26. And we have to subtract that overlap because we counted the 26 within this number and we counted the 26 within that number. So our answer there will be, let's see, 71 minus 26. 71 minus 26. So what's that, 45? 45 out of 81. So you have to be really careful when you're asked an or probability. This intersection part is often forgotten by students. And this one, you might not realize it. Sometimes you'll get like an absurd answer like 91 out of 81, which isn't possible as a probability. But on this one, if you didn't realize, you could just continue on without knowing the error of your ways. 71 out of 81, you might not realize. So you have to subtract that overlap there. The new content today, so everything up to that point isn't really that brand new from previous videos. But the new stuff I'd like to talk about are called conditional probabilities. And a conditional probability, we know we're asked a conditional probability if we have something like this. This is the most common way. There are other ways, but the most common way is a question like D, find the probability that Diamondbacks win given that there are free tacos. The notation there is really important. The notation there is a vertical line, this vertical line right there. We call that such that or given that, And that's telling us our condition, or that's telling us our denominator. So basically how we calculate this, the formula for a conditional probability. Probability of when given free tacos would be the probability of winning and free tacos divided by the probability of that condition, probability that there were free tacos. So the overlap, winning and free tacos, is 26 out of 81. The probability of getting free tacos is 30 out of 81. And then simplifying this, the 81s would divide out basically, and you get 26 out of 30. Now, doing this, if you have winning given free tacos, you could just find where is my free tacos. This is the free tacos line. So our denominator is that total 30. And we have 26 out of 30 was winning given free tacos. I'd encourage you pause the video, see if you can do letter E, find the probability there are free tacos given that the Diamondbacks win. Probability tacos given win, that would be the probability of both of them happening over our condition. Our condition is the winning, probability of winning. So probability tacos and winning is 26 out of 81. Probability of winning was 41 out of 81. So we get an answer of 26 out of 41. Those 81s divide out. So again, you don't necessarily need the formula, though the formula is helpful in some contexts. You would just find your condition. That's the probability of W. So find the event W. And that would be winning. So that's this column. And then you ignore all this other stuff. And then just looking at that column, you have 26 times free tacos were given out of the 41. And then lastly, one more conditional probability here. Find the probability that there are free tacos given that the Diamondbacks win. Oh, and I think I have a typo because I wanted you to do given that the Diamondbacks don't win, which is given that the Diamondbacks lose. So on this one, we'd have the probability of T given not winning. That would be the probability of free tacos and not winning divided by the probability of not winning. So the probability of T and losing, that would be free tacos and losing would be 4 out of 81. So we have 4 out of 81. And then the probability of not winning, that would be 40 out of 81. 40 out of 81. So that looks like it's going to be 4 over 40, or 1/10. So just looking at the table, we have not winning. So I'm looking just at this column. I'm ignoring all these other numbers here. And I would have 4 times out of 40, they were free tacos, yet they lost the game. So there can still be free tacos when they lose the game. Free tacos is if they score 6 or more runs. So that just means they scored a lot of runs, but they lost the game, sadly. So these conditional probabilities help us answer questions like these. Are the events T and W independent? So if they're independent, then knowing, for instance, so like knowing T, that there's free tacos, does this give us more information about the likelihood of them winning, the likelihood of W? So for instance, if I told you, hey, the Diamondbacks, there were free tacos that were given away, does that give you an idea that they're more or less likely to win, to have won the game? So one way that we can calculate this is if they are independent, then this probability, knowing that they win, given that they win and there are free tacos, there's a 63% chance. So given that they win, what are the chances they're free tacos? 63%. If I compare that with this probability, which is 10%, So if I compare these two values, it looks like it's way more likely that free tacos are given away if they win the game compared to if they lose the game. So we would say that we need more space here, but we would say the Diamondbacks are way more likely to give free tacos, or to like earn free tacos for their fans when they win, which is at 63%, than when they lose, which is only 10%, right? And hopefully that makes sense. If the team scores a lot of runs, they're probably more likely to win. And because they've scored more runs, there's more likely to be a chance to get free tacos. So we can compare one way to determine what's called independence. One way to determine independence is to compare these two probabilities. Probability of free tacos when they win versus probability of free tacos when they lose. If those probabilities are equal, then we say that's independent. If the probabilities aren't equal, then we say, well, they're not independent of each other. Knowing one gives us additional information about the likelihood of the other occurring. And then one last term, mutually exclusive. Mutually exclusive events are two events that cannot both happen at the same time. So visually, mutually exclusive events would be a Venn diagram where there's no intersection. There's no overlap. No intersection. No overlap. So are T and W mutually exclusive? We'd say no, because the probability of T and W does not equal 0. If it equals 0, then they're mutually exclusive. If it doesn't equal 0, then they're not mutually exclusive. So I'd like to show you some formulas to talk a little bit more about independent, how you can tell if events are independent. If events are independent, then this formula is true. This is basically the definition of independent events. If the intersection of the two events equals the probability of A times the probability of B. If they're not independent, then that second probability is a conditional probability that changes because of the lack of independence. And then two other formulas. I would encourage you to memorize one or both of these. If this formula is true, then the events are independent. Or if this formula, this is the one we basically just used, it just has a C for complement right there. If either of those are true, then the events are independent. And then I gave you the definition of mutually exclusive events is the probability of the overlap of A and B equals 0. So let's use some of these to talk about independence and being mutually exclusive. So given probability of W is 0.2, probability of C is 0.17, and the probability of W and C, so this little union sign, equals 0.06, are the events mutually exclusive? Are they independent? Well, we would say they're not mutually exclusive since the probability of W and C does not equal 0. So if it equals 0, they're mutually exclusive. So just this fact right here tells us that they are not mutually exclusive. They both can happen at the same time. W and C can happen at the same time. They're not excluded from each other. To determine independence, let's see if does the probability of W and C equal, question mark, the probability of W times the probability of C. This is using this formula to determine if those are equal to each other, then we'll say yes, they're independent. So is 0.06 equal to 0.2 times 0.17? That doesn't look very promising. Let's see, 0.2 times 0.17. That equals 0.06 does not equal 0.34. So we would say they're not independent. The next one we have, given probability of A is 0.6 and probability of B is 0.4, and the probability of A and B is 0, are they mutually exclusive? Well, we'd say yes, since A and B can't occur at the same time. So this is basically the definition of being mutually exclusive. So visually, we would have A is here, B is here, and there is no overlap, so they're excluded from each other. Social distancing for A and B. Are the events independent? Well, does the probability of A and B, does that equal the probability of A times the probability of B? Does 0 equal 0.6 times 0.4? No. So we would say they're not independent. A and B are not independent events. And really, if you ever have mutually exclusive events, then you will not have independent events. So you can be one, but you can't be both. You can be mutually exclusive, but if that's the case, you can't be independent. If you're independent, you can't be mutually exclusive. Okay, so let's look at one more. Are they mutually exclusive? This value right here tells us no, they're not mutually exclusive events. That's pretty fast. Are they independent? Does the probability of A and B equal the probability of A times the probability of B? So A and B is 0.14, A is 0.7, B is 0.2. Multiplying those, these are the same. So yes, A and B are independent events. Independent events. So with probability, it could be tricky for students getting used to the notation and to the various formulas. But if you can remember some of these formulas up there, it'll be very, very good for you. It'll be a nice experience in probability, at least part of it. And I just want to end with a quick summary of comparing mutually exclusive events and independent events. So let's suppose event A is the person's younger than 10 years old, and event B is the person is older than 10 years old. So are they mutually exclusive? Can you be both younger than 10 and older than 10? You can't be both. It's either one or the other. Not at one particular time, you can't be both. So are they mutually exclusive? Yeah, they're excluded from each other. You can't be both. Are they independent of each other? If I told you that someone is younger than 10, does that give you additional information about their likelihood that they're older than 10? And well, it does give you additional information. If it does give you that type of information, then they're not independent. Knowing A about a person, event A about a person, gives you additional information about the likelihood of being event B. And the likelihood basically is that it's impossible. If they're younger than 10, it's impossible that they're also older than 10. So another reason I like this example to use this is just to show you that if you're one of these, if you're mutually exclusive, you cannot be independent. If you know they're excluded from each other, then automatically you know that if you're one, you can't be the other. It's entirely unlikely. It's impossible that you could be the other event. So just a quick summary, you cannot have events that are both mutually exclusive and independent. You could be mutually exclusive, you could be independent, but you can't be both. Or you could be neither, but you cannot be both, unless you have some trivial situation, but that's trivial. Thanks for watching this video. Give me a thumbs up if you actually made it this far through the video. See you next time. Thanks for watching.